Welcome to the Journey Shake Chem. Please do the 2 warm-up questions to the best of your ability, and you may need to use your notes to answer these. And I'll see you in a moment. A volatile liquid has 4 general characteristics that we've discussed. They have a high vapor pressure, a low boiling point. They have weak intermolecular forces of attraction, or IMFAs, and they evaporate easily. Those are characteristics that we have that describe a volatile liquid. An example of that would be like fingernail polish remover, and that's called acetone. Or rubbing alcohol. Rubbing alcohol is actually isopropyl alcohol, or propanol. So it comes in a variety of different names. But those are liquids that if I were to leave them out without a top, they would evaporate all away. And of course, gasoline is our example that we used in our notes. And those are some examples of the ones that we have around the house. In number 2, we are trying to find out the exothermic or endothermic energy changes with these phase changes. And the first one, actually what I like to do is draw the little diagram. That helps me to know which way I'm going. So we begin in solid, we go to liquid, and then we go to gas. And the way that I remember which one it is that when I'm boiling water, I have to add heat, and therefore it is endothermic in that direction. And in the reverse direction, it is exothermic. And the first one is for melting, and melting is where the liquid is changing to the solid is changing to the liquid, and it is endothermic. We are melting, we're going from solid to liquid. Then freezing would be going from the liquid to the solid, and that is exothermic. And we wouldn't think that it would be exothermic, that we'd actually release heat when we are freezing ice. And then we have boiling, and boiling would be liquid to gas, and it is endothermic. We discussed that one at the beginning. And sublimation is when the solid goes directly to the gas, and that would also be endothermic. So this little diagram helps a lot. Now we're going to learn how to use the heating curve and solve a problem. So I have a problem for you to copy that was right below the warm-up. So hopefully you copy that one down, and we'll discuss it in a moment. A heating curve helps us to understand what's going on as ice melts and changes to steam, and then we increase the temperature of the steam. We can only have either a temperature change or a phase change. And so where I have listed ice, water, and steam, that is where the temperature is increasing. The plateau area is where the phase change is happening. The temperature actually stays the same, and all of the energy that's being put in there goes to changing the phase of the substance from whether it's a solid to a liquid or a liquid to a gas. All the energy goes into changing that phase. And the energy to change it from solid to liquid would be called the heat of fusion, and that is 6.02 kilojoules per mole. Now we are doing problems only with water, but the process would be the same with any other substance. You would just have to know these numbers for that specific substance. To change water from a liquid to a gas, we have the heat of vaporization, and that is 40.7 kilojoules per mole. And therefore, when we boil water, once it's boiled and becomes steam, it has to contain all this additional energy. So steam at the same temperature of 100 degrees Celsius has a lot more energy than boiling water at 100 degrees Celsius, because it has all this additional energy that was required to overcome those attractive forces between the molecules and change them from a liquid to a gas. So it would do much more damage as steam than it would as boiling water. Now, when we have temperature changes, we're going to have to use these numbers. And so these numbers here are for the temperature changes. And I use a little abbreviation of just TC. And we use these numbers here when we have a phase change. And I use a PC for that. Now, water has a different specific heat capacity, and what specific heat capacity is how much heat the substance can hold for 1 gram to change 1 degree Celsius. That's why it's per gram degree Celsius. So ice can hold 2.09 joules of heat for each gram 1 degree Celsius. Liquid water is 4.18, and that's why we really like it in calorimeters, because it has such a large specific heat capacity that when you live on the coastal areas, it takes a lot of heat to change the weather and the temperature, because the water absorbs a lot of the heat, and therefore it's a more moderate area around the coastlines. Steam is only 1.84 joules per gram degree Celsius. So an easy way to remember these numbers is if you remember the middle one, which we've had a lot in last semester, 4.18, if I divide that by 2, I get 2.09. Then if I take this number and I take the 4 and put it in the back, I get steam. So that helps a little bit to remember those specific heat capacities for water. And then the heat of fusion, we have our 6.02, but it's not times 10 to the 23rd, it's just the 6.02. And there's just no simple way of remembering that just by using it, but we'll have some practice doing lots of problems. These are the numbers that I need to use in order to solve a problem. And you copy that problem, and now I'm going to work out that problem. Well, the problem was that we had a big piece of ice that was 1.35 kilograms. And I'm going to do a diagram first where I'm starting with my ice, and the ice is at minus 12 degrees Celsius. And I'm going to change it to ice at 0, because 0 is as far as it can go, and at 0 it's going to have to go through a phase change. So then I change it to water at 0. So this is a temperature change and then a phase change. And then once I get it to water, I can change its temperature to 100. And then it begins to boil. That would be a temperature change. And then I change it to steam at 100 degrees Celsius. And then I change it to steam at what was the problem? 105 degrees Celsius. So we have a phase change and then a temperature change. 5 steps would be the most that you would ever have. And if you started with water at 25 degrees Celsius, then you would only have a 3-step problem. So it depends on where you're starting and how to do this. However, we're starting with ice. And we have ice at this step, and then we have 2, 3, 4, and 5 steps. And we take each step at a time, and then we add the values for all of them together. The first step, whenever I have a temperature change, I'm going to use the equation that we've had before. And I have a 1.35 kilogram piece of ice, and 1,000 grams is 1 kilogram. Now I will be using this number throughout, so I'm going to go ahead and solve for that number specifically. The change in temperature is 12 degrees Celsius, and the specific heat capacity for ice is 2.09 joules per gram degree Celsius. And I'm also going to go ahead and change it to kilojoules. And this number comes out to be 33.8580 kilojoules. In step 2 is a phase change, and in a phase change I'm going to use my solid to liquid, and it's 6.02 kilojoules, is 1 mole of water, because we're talking only about water. And we have 1350 grams of water. And 1 mole of water is 18.0 grams of water. And therefore, I have 451.5000 kilojoules. And you can see that the phase changes always come out in kilojoules, and that's why I wanted to change my step 1 to kilojoules, so that when I add them all together, they're in the same unit. Step 3 is a temperature change. I have 1350 grams, and I'm changing the temperature 100 degrees Celsius. And the specific heat of water in the liquid form is 4.18 joules per gram degree Celsius, and I will change that to kilojoules. And I come out with 56433 exactly kilojoules. Then I have step 4 is a phase change again, and I have to use the heat of vaporization. And we're going to do a lab tomorrow on the heat of vaporization, and you'll solve for it experimentally. We have 40.7 kilojoules is 1 mole of water, and we have 1350 grams of water, and 1 mole of water is 18.0 grams of water, and I get 3052.500 kilojoules. And the last step is a temperature change, and I have 1350 grams, and we're changing the final temperature 5 degrees Celsius, and the heat for water, the specific heat capacity for steam is only 1.84 joules per gram degree Celsius, and I'm changing that to kilojoules, and I get 12.42 kilojoules. Then I add up all these numbers, and I'm going to squeeze it here in the middle. We have 33.8580 for step 1. Step 2 is 451.5. Step 3 is 564.3. Step 4 is 3052.5. And step 5 is 12.42. And I add those up, and I get 4114.5780. I look back to my original problem, and I have 2 significant digits. Therefore, my final answer is 4100 kilojoules. And that's how we do those heat problems. Now, you've seen the relationship between the heating curve and how we can solve a problem. And you need to remember these numbers for the practice problems, and try to remember them as you're doing them so that you'll have them when you take the assessment. And that will be forthcoming. Tomorrow you have a lab, so get that ready, and you'll like that one. We're going to show and determine experimentally the heat of fusion and the heat of vaporization. Well, that was some fun, and I can't wait to see you tomorrow. Bye.